Look at your hand. Go on. Hold it there in the light. See the lines on your palm, the shape of your fingers, the solid, undeniable fact of it. It feels real, does it not? It feels like a thing, a separate object in a world of other things. You believe in its substance. You trust its weight. You can use it to knock on a wooden table and hear a solid, satisfying sound. A sound that confirms the world. Solid knocking on solid. Thing meeting thing. This belief is the oldest lie. It is the first and most fundamental illusion your senses have sold you, a story whispered to you from the moment you were born. The story of a world made of parts, of pieces, of particles. We are here to unlearn that story. We are here to ask a question that may unravel the very fabric of what you call you. Are particles even real? The answer is not a simple yes or no. The answer is a journey into the heart of a ghost, a dive into an ocean of pure potential. The answer, when you finally hear it, will not feel like an answer at all. It will feel like the universe asking the question right back at you. Everything you have ever been told about the world is wrong. Not wrong in the way a misremembered date is wrong, but wrong in a deeper sense. Wrong at the root. You were taught that if you take any object, your hand, the chair you sit on, the air you breathe, and cut it in half, and in half again and again for a billion times, you would eventually arrive at something indivisible. A final, tiny Lego brick of existence. An atom. And for a time, that was our story. The atomos, the uncuttable. The bedrock of being. But the story was a lie. We found a way to cut the uncuttable. We cracked open the atom and found it was not a solid marble at all. It was a miniature solar system, a vast and lonely void. At its center, a tiny, dense nucleus. And orbiting in that impossible emptiness, a whisper of a thing. An electron. But here the lie deepens. 99.9999999% of that atom you thought was so solid is nothing, is empty space. Think about that. The chair holding you up is not solid. Your hand is not solid. The earth beneath your feet is a phantom, a collection of immense voids held together by forces you cannot see. You are a cathedral of emptiness, a ghost haunting the shape of your own body. This is the first layer of the truth, the first peeling back of the veil. The world is not made of stuff. The world is made of space. But what of that electron? What a nucleus? Surely, here we find our solid ground. Here we find the particle. No, here the illusion becomes a paradox. That electron, that mote of dust in the atomic cathedral, is not a tiny planet orbiting a sun. It has no path. It has no specific location. Until you look for it. Until you ask the universe, where is it? The electron is nowhere and everywhere at once. It is a cloud of probability, a wave of potential, a mathematical smear of what could be, spread throughout its orbital shell. It is not a thing. It is a promise of a thing. When you measure it, when you force the question, the universe answers. The wave of possibility collapses into a single point, a location. For a fleeting, infinitesimal moment, the electron pretends to be a particle for you. It plays the part. But the moment you look away, it dissolves back into the mist of what might be, back into the wave. This is not a metaphor. This is the truth. The fundamental components of your body, of your world, do not have definite properties until they are interacting with something else. They do not exist as things in and of themselves. The solidity you feel is a statistical illusion. It is the persistent chatter of trillions upon trillions of these possibilities collapsing and reforming over and over, so fast that your senses can only perceive the average. You do not feel a particle. You feel the ghost of a conversation between waves of potential. So we ask again, what is a particle? Is it the wave of possibility or the point-like answer we get when we ask? Which is the mask and which is the face? To understand this strangeness, we must travel back. We must stand in a world on the brink of a revolution, a world where our physics was clean, elegant, and starting to show its cracks. The year is 1900. Physics is a palace of certainty. Newton's laws govern the graceful dance of planets and the fall of an apple. Maxwell's equations have unified electricity, magnetism, and light into a single, perfect symphony. It feels to the scientists of the age that the great work is almost done. All that remains is to polish the details, to measure things to a few more decimal places. The universe is a grand clockwork machine, predictable, rational, knowable. Its parts are solid, its rules are clear. But there is a problem, a small, nagging cloud on the horizon of this beautiful, sunny day of classical physics. It is a problem with light itself, a problem with heat, a problem with the color of things that glow. When you heat an object, it radiates energy. It glows, first a dull red, then a brighter orange, then white, then a piercing blue-white. Classical physics could explain this, but only up to a point. When tried to calculate the energy radiated at the highest frequencies, in the ultraviolet and beyond, the math broke. It predicted that any hot object should instantly release an infinite amount of energy. They called it the ultraviolet catastrophe, a polite name for a crack running through the very foundation of their clockwork universe. The equations said that your fireplace, your candle flame, your own warm body should be blasting out lethal, infinite energy. But they weren't. Reality refused to follow the rules. The universe, it seemed, was protecting us from our own mathematics. But how? Into this confusion steps a man who is not a revolutionary. Max Planck is a conservative, cautious physicist. He does not want to tear down the palace of physics. He merely wants to patch the crack in the wall. He spends years struggling with this problem, trying every conventional trick he knows. Nothing works. Finally, in what he later called an act of desperation, he tries something radical. He doesn't even fully believe it himself. He proposes that energy is not emitted smoothly, like a continuous stream of water from a tap. What if, he suggests, energy can only be emitted in tiny, discrete packets, like water being thrown one bucket at a time, little bundles of energy. He calls these packets quanta. He doesn't think they are real. He sees it as a mathematical trick, a fudge factor to make the equations work. But they do work, perfectly. His new formula precisely predicts the glow of a hot object, taming the ultraviolet catastrophe completely. He has solved the problem, but he has also given birth to a monster. He has planted the seed of a new reality, one that will dismantle the clockwork universe piece by piece. The idea that energy, the very flow of action in the universe, is chunky and not smooth is the first hint that reality is not what it seems. This mathematical trick, this quantum, refuses to go back in its box. A few years later, a young patent clerk in Bern, a man named Albert Einstein, takes Planck's desperate idea and declares that it is not a trick. It is real. Einstein, our visionary, looks at another puzzle, the photoelectric effect. When you shine light on a piece of metal, it can knock electrons loose. But curiously, the brightness of the light doesn't determine whether electrons are freed, only its color, its frequency. A dim blue light can free electrons where a blindingly bright red light cannot. This makes no sense in a world where light is a wave. A bigger wave should have more energy and hit harder. Einstein says, Planck was right. Light itself is made of these quanta, these particles of light. He calls them photons. The blue light photons are individual, high-energy packets, like tiny bullets. The red light photons are lower-energy packets. It doesn't matter how many low-energy bullets you fire. If none have enough energy to do the job, nothing happens. Suddenly, the particle is back. Light, which for a century had been proven to be a wave, is now acting like a stream of tiny particles. This is the core of the initial paradox. Is light a wave, or is it a particle? Experiments could prove both. If you shine it through two narrow slits, it creates an interference pattern on a screen behind, a pattern of light and dark stripes that can only be created by waves overlapping and canceling each other out. This is wave behavior, undeniable. But if you shine that same light on a metal plate, it knocks out electrons one by one, like tiny billiard balls. This is particle behavior, undeniable. The universe is presenting two contradictory faces. It is a wave. It is a particle. It is both. It is neither. This is the moment the old world dies. The clockwork universe, with its solid parts and predictable rules, is shattered. We have entered a new realm, a ghostly, uncertain world, the world of the quantum. And if light, the purest form of energy, can be so schizophrenic, what about matter? What about the electron? What about the stuff you're made of? This is where the story truly becomes strange. A young French aristocrat, a prince named Louis de Broglie, a student of history who turned to physics, makes a suggestion of breathtaking symmetry and strangeness. If waves like light can act like particles, he posits, then maybe particles like electrons can act like waves. Maybe everything has a wavelength. Your hand, the moon, an electron. It seems like a poetic fancy, a philosophical musing. But it is tested. Scientists fire single electrons, one at a time, at a barrier with 2 slits. The very experiment that proved light was a wave. If the electron is a particle, a tiny ball, it must go through one slit or the other. Over time, you would expect to see 2 bands on the detector screen behind the barrier, corresponding to the 2 slits. A simple, common-sense result. That is not what happens. Each individual electron hits the screen at a single point, like a particle. But as you fire more and more electrons, a pattern begins to emerge from these individual impacts. A pattern of light and dark stripes. An interference pattern. The pattern that only waves can make. Let this sink in. Each electron is fired alone. There is nothing else for it to interfere with. And yet, it behaves as if it is a wave that has gone through both slits at the same time, interfered with itself, and then decided where to land on the screen based on that interference. The particle knows. Somehow, the single electron knows that both slits are open. If you close one slit, the interference pattern vanishes, and you get a single band, as you'd expect from a simple particle. Open it again, and the pattern returns. The electron is not a particle that has a wave. It is not a wave that pretends to be a particle. It is something else, something for which we have no word in our daily language. The poet-scientist emerges, trying to capture this ghost in a bottle. Erwin Schrödinger devises a beautiful equation, a wave equation, that describes the electron not as a point, but as a wave function. This wave function contains all the information about the electron, its energy, its momentum, but not its position. Its position is spread out, a cloud of probability, just as we discussed. At the same time, another brilliant young mind, Werner Heisenberg, our radical, takes a different path. He abandons all attempts to visualize what is happening. He says we must give up on pictures of orbits and waves. All we can know are the results of our measurements. Physics, he claims, is not about what the universe is, but what we can say about the universe. From this comes his famous uncertainty principle. It is not just that we are clumsy and our measurements disturb things. It is a fundamental law of nature. You cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you know one, the less precisely you know the other. It's a trade-off baked into reality itself. If you pinpoint the electron's location, its momentum becomes a complete blur. If you measure its momentum exactly, its location dissolves into a wave spread across the universe. The particle is a phantom. It refuses to be pinned down. It refuses to be a simple thing. It exists only in relationship to the questions you ask it. Ask it a where question, and it gives you a location. Ask it a how fast question, and it gives you a momentum. But you can never ask both at once. The universe will not allow it. This is the state of things. The new physics, quantum mechanics, is born. It is absurd, it defies all common sense, but it is unbelievably successful. It predicts the behavior of atoms, the nature of chemical bonds, the functioning of lasers and transistors. The entire modern world is built on its ghostly foundations. Yet the central question remains, gnawing at the heart of science. What are these particles? What is an electron, or a photon, or the protons and neutrons in the nucleus of the atom? To find out, we have to go deeper. We have to build machines, cathedrals of science miles long, to smash these ghosts together and see what other, smaller ghosts spill out. We enter the age of the particle zoo, smashing protons together at immense energies. Physicists found a bewildering array of new, fleeting particles. Hundreds of them. They had strange names like pions and kaons and lambda particles. None of them seemed fundamental. They were all unstable, decaying into other particles in fractions of a second. The world of the small was not simple and elegant. It was a chaotic, overgrown jungle. And so the search for the real building blocks continued. Two physicists, Murray Gell-Mann and George Zweig, independently proposed a new layer of reality. They suggested that many of these new particles, including the familiar proton and neutron, were not fundamental. They were made of even smaller, more elemental things. Gell-Mann, a lover of language and literature, needed a name for these hypothetical constituents. He found it in a whimsical line from James Joyce's novel, Finnegan's Wake. 3 quarks for muster mark. Quarks. The name was playful, almost nonsensical, and the properties he assigned them were even stranger. He proposed they had fractional electric charges, like 1/3 or 2/3 of an electron's charge, something never before seen in nature. The theory was a work of beautiful organization. It was a taxonomy of the strange. It took the messy particle zoo and arranged it into a simple, elegant family tree. All these complex particles were just different combinations of a few types of quarks. A proton was 2 up quarks and 1 down quark. A neutron was 1 up quark and 2 down quarks. It was perfect. There was just one problem, a very big problem. No one could find a quark. They smashed protons with incredible violence, hoping to knock a single quark loose. But they never came out. It was like trying to break a bar magnet to isolate a north pole from a south pole. You can break it in half, but you just get 2 smaller magnets, each with its own north and south pole. You could never, ever get a quark by itself. This led to a new and profound rule of the unseen. A force that governs these quarks is called the strong nuclear force, but it behaves like nothing else we have ever encountered. The force of gravity or electromagnetism gets weaker with distance. Pull 2 magnets apart, and the force between them diminishes. It's intuitive. The strong force does the opposite. The force holding quarks together inside a proton is actually quite weak when they're close together. They rattle around inside, almost freely. But if you try to pull one away, the force gets stronger, and stronger, and stronger the farther you pull. It's like a cosmic rubber band. The more you stretch it, the harder it pulls back. If you pull with enough energy to finally snap the band, something incredible happens. The energy you poured into the system, the energy holding the stretched band, converts into mass, following Einstein's E equals mc squared. And from that pure energy, a new quark and its antimatter partner, an antiquark, are born out of the vacuum. The new antiquark pairs with the quark you were trying to pull out, forming a new, stable particle. The new quark stays behind with the original 2. You don't end up with a free quark. You end up with the original proton and a brand new particle. You can never win. The universe forbids you from ever seeing a quark alone. It is a prisoner for life, forever confined within a larger particle. So we ask the question again, with a new and unsettling urgency. If you can never, ever see one by itself, if it is fundamentally impossible to isolate one, in what sense is a quark real? We have experimental evidence. We have shadows on the wall. When we fire electrons at protons, they scatter in a way that suggests there are 3 tiny hard points of charge inside. We see the fingerprints of quarks in the mathematical debris of our collisions. We see the jets of new particles created when we snap that cosmic rubber band. We have all the indirect evidence in the world, but we can never hold one. We can never point to one. A quark is not a thing. It is a component of a relationship. Its existence is defined by its unbreakable bonds to other quarks. Its reality is a shared reality. The particle is demoted again, first from a solid ball to an empty atom, then from a point-like electron to a wave of probability, now from a fundamental brick to a permanent prisoner that cannot exist on its own. And the story doesn't end with quarks. We have a whole family of these fundamental phantoms, the standard model of particle physics. It is our current best map of reality's bedrock. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Each name a whisper of the whimsy and strangeness of this world. There's another family of particles called leptons. This family includes the familiar electron and its heavier, unstable cousins, the muon and the tau. It also includes the most ghostly particle of all, the neutrino. Neutrinos are born in the heart of stars and in radioactive decay. They have almost no mass. They have no electric charge. They barely interact with anything. Trillions of them are streaming through your body, through the entire Earth, every second, and they do not notice. They're the closest thing to nothing that is still something. Pure, unadulterated potential for interaction, almost never realized. And then there are the forces, the rules of the game. In this new picture, forces are not some mysterious, invisible influence. They're also particles. When 2 electrons repel each other, they're not being pushed by an invisible field. They are exchanging a particle, a photon, a messenger particle of the electromagnetic force. The strong force that binds quarks is carried by particles called gluons, because they glue the quarks together. The weak force, responsible for radioactive decay, is carried by W and Z bosons. Reality is not a stage with actors on it. It is a dynamic, constant exchange of messages. A conversation. The particles of matter are the nouns. The particles of force are the verbs. And you cannot have a sentence with only nouns. This is the standard model. 12 particles of matter, 6 quarks, and 6 leptons, and 4 forces carried by their own messenger particles. It is astonishingly successful. It has been tested for 50 years, and its predictions have been confirmed with breathtaking precision. And yet, it tells us that all these fundamental entities are not things, but excitations. Here we must take the final step in demolishing our idea of a particle. The most modern and perhaps most accurate view of reality is called quantum field theory. In this view, the most fundamental thing in the universe is not a particle at all. It is a field. Imagine the entire universe is filled with invisible, intangible fields. There's an electron field filling all of space and time. There's an up quark field, a photon field, a field for every fundamental particle. These fields are usually dormant, quiescent, like the smooth surface of a perfectly still lake. They are the vacuum. But the vacuum is not empty. It is a sea of potential. What we call a particle, an electron, for instance, is not a thing that moves through the electron field. It is a localized vibration in the field, a ripple, a tiny, temporary knot of energy. When you see an electron, you are not seeing a tiny ball. You are seeing the electron field get excited at that particular point. A particle is just a quantum of a field, a little bundle of its vibration, just as a photon is a quantum of the electromagnetic field. This changes everything. Particles are not fundamental. Fields are. Particles can be created and destroyed. You can smash 2 photons together and create an electron and its antimatter twin, a positron. You are not creating matter from light. You're taking a vibration in the photon field and using its energy to create 2 vibrations in the electron field. The particles are not conserved. The fields are eternal. The particles are just the temporary notes that the fields can play. The universe is not a collection of little marbles. It is a grand cosmic symphony of vibrating, interacting fields. The particles are just the brief, resonant notes in that symphony. They appear, they interact, they vanish back into the silent potential of the field. You're not a collection of particles. You're a collection of standing waves. A complex, stable pattern of vibrations in the quantum fields. A song that has managed to sustain itself for a few decades. But if this is the case, if particles are just fleeting ripples, then some of the deepest paradoxes become even more profound. Let us return to the wave-particle duality, the 2-slit experiment, the electron that goes through both slits at once. In the field view, this makes a new kind of sense. The electron is not a particle. It is a wave in the electron field. The wave naturally passes through both slits, interferes with itself, and creates the pattern. The mystery remains why, when we measure it, the wave gives up its wave-like nature and delivers all its energy to a single point, creating the illusion of a particle. This is the measurement problem, the moment of collapse, the transition from the ghostly world of potential to the concrete world of the actual. Why does asking a question of the universe force it to give a single, definite answer? No one knows. This is the beating, black heart of the quantum mystery. It is the point where physics touches something else. Philosophy, consciousness, the nature of information itself. The role of the observer, of the measurement, seems to be to take this smear of probabilities described by Schrödinger's wave and force it to choose. Be here, we say, with our detector, and the wave obeys, becoming a point. What is so special about measurement? Is it the interaction with a large, classical object? Is it the involvement of a conscious mind? Great scientists have argued about this for a century, and we are no closer to an answer. It is as if reality is a dream, and observation is the act of waking up a tiny piece of it into a temporary, solid-seeming state. And the paradoxes only get deeper. We must now speak of the phenomenon that Einstein, the reluctant grandfather of this strange world, called spooky action at a distance. We must speak of entanglement. It is possible to create two particles, two vibrations in a field, in such a way that their properties are linked. For instance, you can create two electrons whose spin is correlated. Spin is a quantum property roughly analogous to a tiny magnet. It can be up or down. If you create an entangled pair, you know that if one is spin up, the other must be spin down. And vice versa. Their fates are intertwined. This doesn't sound so strange yet. It's like putting one black marble and one white marble into two separate boxes, mixing them up, and sending one box to the other side of the galaxy. Before you open your box, you don't know which color you have. But the moment you open it and see a white marble, you instantly know, faster than the speed of light, that the other box contains a black marble. That's simple correlation. But quantum entanglement is far stranger. The marbles are not black or white until you look. Each particle, before measurement, is in a superposition of both spin up and spin down at the same time. The wave function for the system just says the spins are opposite. It doesn't say what they are. Now, you take your particle, and your friend takes the other one to a distant star. You both wait. At a prearranged time, you measure the spin of your particle. Your measurement forces it to choose. Let's say it chooses up. Instantly, across light years of empty space, the other particle, which was also in a state of fuzzy potential, immediately collapses into the down state. There is no signal sent. Nothing travels from your particle to the other. And yet, they are connected. They are, in a deep sense, not two separate particles. They are a single entity, a single wave function that happens to exist in two different places. Touching one part of it instantly affects the other part, no matter how far apart they are. This violates what Einstein called the principle of locality, the common-sense idea that an object can only be influenced by its immediate surroundings. An action here cannot instantly affect something over there. It seems to be the most fundamental rule of the universe. And quantum mechanics calmly says that this rule is wrong. The universe is not local. What does this mean for our concept of a particle? If two particles light years apart can be a single system, where does one particle end and another begin? What does separation even mean? The idea of a particle as a distinct, individual entity is completely and utterly destroyed. A particle is not an object. It is a focal point of a web of relationships that can span the entire cosmos. Its properties are not its own. They're defined in conjunction with its entangled partners, with the act of measurement, with the questions being asked of it. Reality is not made of things. Reality is made of relationships. The illusion runs deeper still. We have talked about the vacuum as a sea of dormant fields, but it is not truly dormant. Heisenberg's uncertainty principle applies to energy and time as well. You can't know the exact energy of a system for a given slice of time. This means that for very, very short periods, the vacuum can borrow energy from nowhere. And with that borrowed energy, it can create particles. Out of the absolute nothing, particle-antiparticle pairs can pop into existence. An electron and a positron, a quark and an antiquark. They exist for a fleeting moment, an impossibly short time, before they find each other and annihilate, paying back the energy debt to the vacuum. These are called virtual particles. They're not real in the sense that they can be measured directly. They're the churning, frothing foam on the surface of the quantum fields. But their effects are real. They are measurable. They subtly change the properties of the real particles we see. The mass of an electron, its charge, these values are slightly altered by the constant swarm of virtual particles winking in and out of existence around it. The electron is not just a ripple in its own field. It is a ripple perpetually dressed in a shimmering, ever-changing cloak of other, ghostly ripples from every other field in the universe. The vacuum is not empty. It is a boiling cauldron of potential, of ghosts being born and dying in the blink of a cosmic eye. What we call a particle is just a long-lived, stable ripple in this chaotic sea. But the sea itself is the true reality. Let us stand back now and look what we have found. We started with a simple, solid object, your hand. We have journeyed through its substance and found nothing solid. We found atoms that are almost entirely empty space. We found electrons that are not objects but clouds of probability, waves that only pretend to be particles when we look. We found that the protons and neutrons are bags of quarks that can never be seen alone, held together by a force that grows stronger with distance. We have found that these quarks and all other fundamental entities are not particles at all, but temporary vibrations in universe-spanning fields. We have found that these vibrations are linked in spooky, non-local ways that defy our sense of space and separation. We have found that the very vacuum of space is a riot of virtual particles, a sea of ghosts from which our reality is just a stable foam. So we must now face the question head-on, not as a question of physics, but as a question of philosophy, a question of what it means to be. What does the word real even mean? If by real, you mean a thing that exists independently, with its own definite properties, separate from everything else, then no. Particles are not real. Nothing is real in that sense. If by real, you mean something solid and permanent, then no. Particles are not real. They are fleeting, transient, and can be created from pure energy. If by real, you mean something that can be isolated and pointed to, then no. Many particles, like quarks and gluons, can never be isolated. Their reality is only as part of a collective. The classical idea of reality, a world of independent objects, is dead. It was a useful fiction for a species living on a macroscopic scale, but it is not the truth. The universe is not a machine made of parts. It is a holistic, interconnected whole. It is a web of relationships. Nothing exists in isolation. And what does this mean for you? You, this collection of thoughts and feelings and memories that you call a self. You too are made of these ghosts. You are a trillion patterns of vibration in the quantum fields. A complex harmony. You're not made of stuff. You're a process. You are an event. You are a song the universe is singing. Your sense of being a solid, continuous self is the same illusion as the solidity of your hand. It is an average, a statistical effect of an unbelievably complex dance of potentials and probabilities collapsing into fleeting moments of actuality. Where does the quantum world end and your world begin? There is no boundary. The strangeness is not confined to the subatomic realm. It is the foundation of everything. You're breathing it. You're living it. The firmness of the ground beneath you is an electromagnetic conversation between the electron fields in your shoes and the electron fields in the pavement. The light you see is a stream of vibrations in the electromagnetic field, being absorbed by the fields in your retina. Every thought in your brain is a cascade of chemical and electrical signals, which is at its root the exchange of messenger particles, the collapse of wave functions, the dance of quantum fields? Could it be that consciousness itself, the very fact that you are here experiencing this, is a macroscopic quantum phenomenon, an emergent property of this web of relationships? This is pure speculation, the frontier where physics gives way to poetry. But think about it. Consciousness seems to be a unifier. It takes a flood of disparate sensory data, sights, sounds, feelings, and weaves them into a single, coherent experience, a whole. Quantum mechanics describes a world that is also, at its heart, a unified whole, masquerading as separate parts. Is it so crazy to think that one might be a reflection of the other? That a conscious being is a system complex enough to experience its own quantum nature as a unified self? A stable resonance in the symphony of fields that has become aware of the music. Perhaps the act of observation, the collapse of the wave function that so puzzles physicists, is not something that only happens in a lab. Perhaps it is happening constantly within you. Perhaps your consciousness is, in some way, a continuous act of measurement, of collapsing the infinite potential of the universe into the single, actual story of your life. We do not have the answers. We may never have the answers. Science is a method, a process of asking better questions. It is not a book of final truths. So let us return, one last time, to our first question. Are particles real? We have seen that they are not things. They are not independent. They are not permanent. They are not solid. But they are not nothing. Their mathematical description is the most successful theory in the history of science. Their behaviors build the world we know. Their interactions are the source of stars, of planets, of life. Perhaps the question is wrong. Perhaps the word real is the problem. It is a word we invented for a world of rocks and trees and lions. A world of middle-sized objects moving at middle speeds. We're trying to apply a word from our savannah-based intuition to a realm it was never meant to describe. A particle is not real or unreal. A particle is a human concept. It is a name we give to a particular kind of interaction between a quantum field and our measuring device. It is a verb that we have mistaken for a noun. The final metaphor, then, is not one of things at all. It is one of language. The quantum fields are the alphabet of the cosmos. The rules of physics, the forces, are the grammar. The particles are the words that this grammar allows to be formed from the alphabet. And the universe, all of existence, is the epic poem that is written with this language. You are a stanza in that poem. A particle is not a thing, but a manifestation of a rule. It is a whisper in the equations made tangible for a moment. It is the universe talking to itself. So when you look at your hand again, do not see a solid object. Do not see a collection of tiny billiard ball particles. See what is truly there. See the vast, shimmering emptiness. See the symphony of vibrating fields. See the web of relationships connecting you to the farthest star. See the churning sea of virtual ghosts in the vacuum between your atoms. See the wave of potential that you are, collapsing and reforming with every breath, with every thought. You are not a thing in the universe. You are the universe experiencing itself as a thing. The particle is not real in the way you once thought, but its unreality, its ghostly, relational, potential nature is the very reason that you are here to ask the question. Reality is so much stranger and so much more beautiful than your senses ever told you. And the mystery does not end. It is only just beginning.